Hello everyone, and thank you for joining today's Code Along. My name is Reese and I'll be your moderator today. We're going to kick off today's session in a couple of minutes at the top of the hour. We're just waiting so everyone has a chance to join. In the meanwhile though, we'd love to hear from you, so let us know where you're joining from using the chat or the comments depending on what platform you're watching from. And yeah, tell us something that you'd like to get out of today's webinar. If you have any questions at any point throughout the session, then please let us know using the chat and the comments. And yeah, I've got a few more bits of information for you if you're planning on coding along with us. So first of all, make sure you register for the event so you can get the recording and the resources sent to you so you can watch it back. I will be sending a link to that in the chat shortly, but you can also head to datacamp.com/webinars. And for the session today, you'll want to have Python version 3.9, 3.10 or 3.11 installed so you can code along with us. And I'll also be sharing a couple of links so you can code along with us as well. So keep your eyes peeled on the chat. Brilliant. I'll be sending that link so you can register for the event today. And yeah, keep your eyes peeled for anything else. But yeah, let us know where you're joining from. Hello everyone, and thank you for joining today's Code Along. My name is Reese and I'll be your moderator today. We're going to kick off today's session in a couple of minutes. We're just waiting so everyone has a chance to join. In the meanwhile though, we'd love to hear from you, so let us know where you're joining from using the chat or the comments depending on what platform you're watching on. And yeah, tell us something that you'd like to get out of today's session. If you haven't already, then please do register for the event today so that we can send you the recording and any other goodies that we've got lined up. I've sent a link to that in the chat, but you can also head to datacamp.com/webinars to get that as well. To code along with us today, you'll want to have Python version 3.9, 3.10 or 3.11 installed, and I'll also be posting a link in the chat shortly so that you can code along with us and yeah, get set up. If you have any questions as well, let us know using the chat, and yeah, we'll be there to answer them at the end of the session. Brilliant. I'll be back to repeat these messages once more for any new joiners, but until then, enjoy the background music. Hello everyone, and thank you for joining today's Code Along. My name is Reese and I'll be your moderator today. We're going to kick off today's session in about 20 seconds or so. We've just been waiting so everyone has had a chance to join. Let us know where you're joining from using the chat or the comments, and yeah, tell us something that you'd like to get out of today's webinar. If you haven't already registered for today's event, then check out the link that I sent in the chat or head over to datacamp.com/webinars, and yeah, you can get the recording and resources sent to you. Note, if you are going to code along with us today, make sure you have Python version 3.9, 3.10 or 3.11 installed, and yeah, you'll be able to code along with us safely. Brilliant. I will also be sending links so you can code along with us in the chat, so keep your eyes peeled for those. But with that, I think that's pretty much everything from me. So now I'll hand over to your host for today's session, Richie. Richie, please take it away.
Hi there, data scamps and data champs. This is Richie. So, two of the most important use cases for generative AI that have emerged are better chatbots and better search. And so in addition to large language models, both of these use cases take advantage of a second technology, namely vector databases. So in fact, anytime you need to make sure that your LLM isn't going to hallucinate, or you need to provide factual information, then you need to make use of a technique called retrieval augmented generation. So today we're going to learn how to do that using Milvus, which is a production-grade open source vector database. Now, before we begin, just a heads up that we're going to be using an AI framework called Llama Index today, and I ran out of time getting it to work with Workspace. It's very picky about the versions of Python it's using, so apologies for that. Now, I plan to try and get that fixed in the near future. But for today, if you want to code along, we're going to send out some links to the notebooks, but if you want to code along, you're going to have to use an alternative notebook platform. Otherwise, you can just watch along today, and once we get the recording, and it works in Workspace, we'll have that available to you. Anyway, that aside, our guest today is Yujian Tang, a developer advocate at Zilliz, the maker of Milvus. So in his role, he spends most of his days teaching people how to make use of vector databases and AI. And Yujian previously worked at Amazon developing machine learning products, and he's also founded 2 startups. So very experienced there. With that, over to you, Yujian.
Cool. Yeah, thanks for that intro. Thanks for that intro, Richie. Yes, so we'll be using Llama Index and Milvus today. I'm going to start off by giving a quick presentation about retrieval augmented generation and some of the flavors, and then we'll dive into the code. And so with the code, there's going to be a couple of notebooks that we're going to look at. One is a very simple, just how do you get started with Llama Index and Milvus? How does it work? And then we'll get into a more complex, what is an enterprise grade or enterprise level kind of architecture or enterprise level proof of concept look like? And so that'll be the multi-document querying. So yes, let's get started with the slides. So hopefully you guys can see these slides here. I can't see the slide window when I'm going through the slides, so I will check back to make sure everything is working. But today we're going to be talking about retrieval augmented generation and its flavors. My name is Yujian Tang, and there I have a QR code to the right where you can scan that if you would like to add me on LinkedIn. I'll give you a little bit of my background so you can kind of get an understanding of where I'm coming from and what the framework that I'm approaching this kind of topic with. So as Richie said, I was previously at Amazon. I actually started my career doing a bunch of computer science coding contest type things. And so in high school, I started interning at IBM, and then I went on to college where I studied machine learning, and I published a few different papers. And that's actually how I ended up at Amazon, where I worked on their AutoML system. So I've been in ML infrastructure for a while. As Richie said, I've started 2 companies, and I have run them both into the ground, and I am not the CEO at Zilliz, so I will not be doing that with this company. And now that's my cue to talk a little bit about Zilliz. So Zilliz was founded about 6 years ago in Redwood Shores, California. We maintain a bunch of open source projects. We're a very open source first kind of company. And probably the main open source projects that you want to pay attention to here are Milvus, which is the open source vector database, which, as Richie talked about, is a key technology in this new LLM stack and is very, very helpful in driving these new retrieval chatbot type things. And the main value prop of using a vector database is that it does semantic similarity search. And we'll cover that in the presentation if you don't know what that is. We also cover some other open source projects. We'll talk about GPT cache a little bit in this presentation. GPT cache is a semantic cache. It's essentially we used it to reduce our OpenAI costs. And then there's vector database benchmark, which allows you to bring your own data and benchmark many, many vector databases. Okay, so this presentation is going to kind of come in the form of why do you need retrieval augmented generation, especially from the framework, the context, the angle of working with large language models. How does retrieval augmented generation work? What's actually going on underneath the scene? underneath the surface. What does a RAG tech stack look like? So what do you need to build a RAG app? And then we're going to cover a couple architecture examples. So let's get started. Why do you need RAG? Okay, so the basic idea of why you need RAG is, well, there's actually two basic ideas. One is that large language models hallucinate, and the other is that they don't work with your data. But we're gonna kind of cover both. I want to introduce why large language models hallucinate, and then we'll kind of go into how you can solve this issue and how you can solve this with your data. So I'm going to take you guys all the way back to the 1970s really quick here. This is a example of a neural network. And this is a basic deep neural network. And essentially what's going on here is that you're getting some sort of data, you're putting it in, it's doing some sort of calculations, and then it's spitting out some numbers for you that is typically some sort of classification, some sort of prediction, some sort of yes or no, or this is a token or something like that. As we worked with more data, we found that there's two types of neural network architectures that typically that handled our most common data types really well. So number one is images work really well with convolutional neural networks, and text works really well with recurrent neural networks. And so here we're going to be mostly talking about text. Not that vector databases don't work with images, but LLMs mostly work on text. Now I know that GPT-4 has recently come out with an image option, but bear with me here. We're going to take this from a text perspective. Okay, so the reason this image here that that I have on the screen here is an unfolded example of a recurrent neural network. So what this shows you is that over time, recurrent neural networks are able to keep track of tokens over time. You see this xt-1, xt plus 1 kind of thing. This is the different things in, these are the different entries in, what's it called? A sequence. And so one thing we found with recurrent neural networks, though, is that these sequences, we couldn't have them be very long because they would lose context over time. So how do we solve this? Well, we introduced this thing called a transformer. And what a transformer does is it takes the input, your input sequence, and it encodes it into some sort of hidden state. And the hidden state is really just a set of vectors or a matrix, you know. And so this hidden state encodes the tokens and the positional embeddings. So it tells you the context of, A, where are you, as well as what are we currently looking at. And we take this hidden state, this matrix, and we combine it with an additional input, typically referred to as self-attention. And we put this into a decoder, and the decoder combines these as well as, you know, does a bunch of calculations, and it gives you an output. In the case of GPT, that output is going to be the next token or the next word. So GPT is a decoder-only architecture, and the way that it works is essentially you start off by giving it the chicken walked and then having it finish your sentence. Sorry, I'm a little bit burpy. So in this case, it's the chicken walked across the road, and so it'd be the chicken walked, and then GPT would process that, and it would say, okay, out of the data that I've been trained on, out of the data that I've been given, the data that I have, the most common way that I see, or the most common word for the chicken walked, the next word would be across. And then from there, the chicken walked across, the most common word that comes next would be the road, and then road, and then it would end the sentence. And so this is kind of showing you how GPT thinks based on the data that it has access to. So the takeaway here is that large language models hallucinate because they're designed to predict the next token. So how does RAG work? How does this help you? You can inject your custom data on top of an LLM so it doesn't have to predict or guess or think about what could be the right answer for you based on its training data. If you inject a data layer on top of the LLM, you can actually reduce or completely negate hallucination depending on your own setup, your configuration. So I'm going to start off by introducing this concept of semantic similarity. The primary driver of retrieval augmented generation and being able to work with your data is that you can find data that's similar to other data. And so in this slide, all I really want you to get from this slide is that vector embeddings allow you to do math on things that are not originally numbers. Okay, so all you're looking at here is we're going to do math on words. with vector embeddings. And so I'm going to draw your attention to some things, and then we're going to walk through this equation here. So first, I want to draw your attention to these vectors, right? There's two of them. You're never going to see two-dimensional vectors in real life. And then in this math, you're never going to see people literally just straight up do Manhattan distance like this. So also another thing I want to point out is that queen and woman and king and man have the same value on the first axis here, the first dimension here. But this only tells us that these words mean the same thing on that dimension in the data set that it was trained on. Okay. So queen's, woman, the 0.3 does not necessarily refer to any specific quality about the words. It could be just these both the words have 5 letters, and that's why they are assigned this value of 0.3. It could be something very, very abstract. Vector embeddings are an abstract, the dimensions of vector embeddings are very abstract representation of what the words mean. Okay, so let's take a look at how this math works. So we have queen is 0.3, 0.9, and we subtract the word woman, which is 0.3, 0.4, and we end up with 0, 0.5. And we can guess that this means something like royalty. And then we can add the word man to it, which is 0.5, 0.2, and we arrive at king, which is 0.5, 0.7. So once again, the only thing you need to get from this slide is that vector embeddings, such as these sets of numbers, these little lists of numbers, allow you to do math on things that were not initially numbers. Okay. So where do you get your vectors? Where do these vector embeddings come from? Essentially, you start with your knowledge base, your data, and you run it through some sort of deep learning model. And this deep learning model there's a few kind of rules that you have to follow when you're picking this deep learning model. It has to be a model that is trained on the type of data that your document is. So for example, if your document is text data, you're going to want to pick a text model. If your document is image data, you're going to want to pick an image model, right? And then the way we get the vectors is we cut off the last layer of the model, and that's how we get the vectors. And so the dimension of the vectors corresponds to how big the second to last layer of the model is. Once you have the vectors, you can store them in Zillis or Milvus, and that is step 1 to 2 of this image. And then step 3 is actually the same thing. You take some sort of knowledge base or some sort of queries in this case, and you run it through the same model, and you get the same you get your vectors, which should probably be different. And then you compare them against the vectors that are stored in the vector database through an approximate nearest neighbor search, and you'll get your results. Okay, so this is how similarity search works. And the takeaway here is basically that you can inject your custom data on top of large language models, and you can use similarity search to find the right data that you need. So what does the RAG tech stack look like? The basic idea of this section is that RAG apps can be built like computers. And the correspondence here is almost one-to-one. You can use a ChatGPT or any other LLM, and this is your compute power. This is your CPU, your GPU. This is what makes things run, in a sense. And then you have to have a storage engine, and your storage engine here is your vector database, Milvus. It stores your data. It can be your source of truth. And then there's something that we use to tie it all together, which is prompt as code. And so this is where we take prompts that we give large language models, and we treat this almost as code. Despite the fact that it's a non-deterministic output, what we can actually do is we can have this run similar things each time by making the prompt the same each time. So we codify the prompt, and we expect a similar type of output. Okay. So an example of a RAG app would be something like this, which is called OSS Chat. And so if you go to osschat.io, you can find this example app. And the idea behind this is that if you are working in an enterprise, if you are working at a large company, you are going to have hundreds of thousands, and I think hundreds of thousands is actually an underestimate. You're probably going to have millions or tens of millions of pages of documentation. And you want to do something with that documentation, such as be able to search it, right? I mean, there's been a lot of studies that have come out that show that knowledge workers like you and I, we spend nearly 2 to 3 hours a day just looking things up. And I will tell you from personal experience, this is a very common experience, right? And it would be great if I just had a chatbot kind of like this that would just be like, oh, actually what you need is in this section of the wiki and it's detailed right here. And this is the person who wrote it, right? So this is the value of using RAG, is that you can kind of be able to very, very quickly do great retrieval and get the information that you need. And so the takeaway from this section is basically very simple, right? A RAG app can be built like a computer using an LLM for compute, which is with the CPU or GPU. A vector database for your storage. This is your hard drive, your RAM, your HDD, your SSD, whatever. And your prompt is code, which is the interface. The way that you interface with your computer is the prompt, the way that the compute and the storage interface. Okay. So I'm going to run through a couple of architectural examples for you guys, and then we're going to get into the code. So we're going to start with the most basic RAG architecture, which is essentially you start with some sort of query, and it breaks down. It goes to an LLM, and the LLM breaks your query down. And so actually these two LLMs here are mainly for query breakdown, query decomposition. This one is mainly for breaking your query down. So for example, if I ask the question like, which cities in America have the top 3 populations, then you need to break this kind of thing down. You need to be able to be like, oh, okay, I'm looking for American cities. I'm looking for top populations. I'm looking for 3 of them. And what you can do is, let's say you have a database of American cities. Then you go to Milvus, and your LLM searches through this database where all of your data is vectorized, and it looks for these kinds of semantic meanings. So it looks for cities in America. It looks for this population of cities in America, and then it starts to rank them. And then when you get all this information back, the LLM, the second LLM takes that and it turns it into something human readable, and it says the cities in America with the top 3 populations are New York, Los Angeles, and I don't know, something else, right? So that's the basic RAG architecture. So how do we improve this? At scale, we find that it's actually very expensive to be calling an LLM multiple times. And so what we want to do here is add a semantic cache. This is GPT cache is what I was talking about. So we found that when we put our chatbot up, osschat.io, when we were doing a lot of work with it and putting it up, we were running tens of thousands. I think it was like $30,000 of OpenAI credits a month, and we were like, hey, that's kind of ridiculous. And so we were like, let's see how we can reduce this cost. And that's how we came up with GPT cache. GPT cache is a semantic store where your queries will actually go and it will check out your queries first and say, has anybody asked this recently? Is this something that I've seen? Is this something that would be easy for me to just return what the answer is? Do I already have the answer? And if it already has the answer, then it just returns the answer back to you. You don't have to go and ping an LLM or anything else. You just get the answer back from GPT cache. So this is more or less a cost optimization tip. And this is the architecture of what we're going to be building today. So this is the second thing we're going to be building today. The first thing we're going to be building today is going to be a more or less introductory piece. I'm not going to code it up for you, and we're just going to walk along and take a look at it, and then we will code up something a bit more interesting. So let's see. Oh, that's not what I wanted to do. Oh, okay. Let me pull up the GitHub and then I will share that. Okay, here we go. Okay, hopefully this is okay. Yeah, I will zoom in a little bit so we can. Okay. Yeah, this should be fine. Okay. So this is a pretty simple notebook that is how do you use Llama Index with Milvus. Oh, I should give a short introduction of what Llama Index is as well. So LangChain and Llama Index are two very popular LLM app frameworks. LangChain was maybe no longer exactly, was initially more focused on LLM orchestration. And Llama Index was, and maybe is still focused on data retrieval. And so for this example, and these kinds of, these libraries both use each other sometimes. And so in this example, what I'm going to show you is just how do you get Llama Index up and running with Milvus. So we're going to have these installs. And as mentioned earlier, you're going to need Python 3.10, 3.11, 3.9. I really suggest 3.11 or 3.10 if you have it. And then these imports, we're going to need these imports. So we're actually going to use something called just vector store index. So Llama Index has renamed their indexes multiple times now: GPT vector store index, simple vector store index, vector store index. So these are all the same thing. They're just a different name for the same abstraction. And then there's going to be a storage context. And this is how we pass a vector database into our index and our query engine. And there's going to be a simple directory reader, which is cut off. But this is how you read data into Llama Index. And then we're going to get the Milvus vector store because we're working with Milvus. And we're going to run Milvus directly in our notebook through something called Milvus Lite, which was actually contributed by a community member at Milvus. Remember, Milvus is an open source project. So someone who's using Milvus wrote this for us, and that was great. And then we have this is .m is just for managing environment variables, and OS is meant for same thing, managing environment variables. As we can see here, I'm loading up my OpenAI key, and then I'm starting Milvus. So this was run on 2.2.6. You can see that this was run many, many months ago, and we are now on 2.3. And you probably won't actually see that unless I run it verbosely in the exact run today. But the connection is the same. So we're going to just connect to Milvus. We're going to give it the host and the port that it needs. And then we're going to read in the data, and we're going to give it a storage context, which is the vector store, right? So we're going to pass in like, hey, we're using Milvus. This is the Milvus instance that we connected to earlier. We're going to pass it in. Then we're going to have an index. We're going to create our index from the documents that we have. So in our example later, we're going to be scraping some documents. In this example, you can actually find the data that I use here in, oh, no, not data. Maybe it's a citation. Maybe it's directly here. Okay, well, the data is somewhere around here, but it is the Paul Graham essay that talks about who he is and stuff like that. And in order to query it, we have to first initialize it as a query engine. And then we just simply ask, hey, what's going on? What did the author do growing up? And we print out the response. And it tells us, like, growing up, the author wrote short stories programmed on an IBM 1401 and nagged his father to buy him a TRS-80 microcomputer, blah, 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 blah. At the end, it's good to stop the server and clean it up. If you don't do this, you will probably run into like slow starts and stuff like that. Okay, so I'm going to share my notebook. Okay. Can you guys see this? Yes, okay. Oh, I'm going to zoom in a little bit. Hopefully this is helpful. Okay. So the first thing we're going to do here is we're going to run our pip installs. So we're going to pip install Milvus, PyMilvus in case we need it. Let's see, what else do we need to install? NLTK, Llama Index, OpenAI, PyMilvus. Oh, I already got that, sorry. I think this might need requests. I need this python.in if you have variables and requests. So I'm not going to run this because I already did this, but this is probably the first thing you need to run. These are all the libraries that we're going to use. And then if you run into an SSL error with whatchamacallit, llama, no, sorry. With NLTK, you might run into SSL errors, and Llama Index now uses NLTK as a dependency when it comes to very fast token parsing. So this is how you basically are able to do some NLP without the help of an LLM. So here, what we're going to do is we're going to import NLTK. Okay, so what we need to do is we actually need to download two libraries. We need to download stop words and punct. Punct stands for punctuation. And so we need these two libraries from NLTK. And so the first thing we're going to do here is we're actually going to do a SSL verification. So let's see if I can do this. Create unverified HTTP context. Create. Ah, there it is. Wow, nice. Okay. And then SSL.create unverified context. Great. Didn't mean to do that. Okay. So let's see if we have an attribute error. I'm just going to pass. I think if we have another error, we're going to do something else. SSL.create default context, create default HTTPS context. And we're going to do this, and we're going to set this equal to create unverified HTTPS context. Okay. Which is just none, by the way. So NLTK dot download stop words, NLTK dot download punct. And so I should have both of these, so this shouldn't do anything for me. Yes, okay, so this doesn't do anything for my screen, but this is something that you will want to do. And so I will scroll up just so that you can continue to take a look at that for a second, because this is a weird, probably something you don't see very often, is like, how do you do SSL stuff? So in the next section, we're going to import some Llama Index stuff, and we're going to import some LangChain, a LangChain import as well. So let's get to that. So first, we're going to import some things from Llama Index. Do I do braces here, or do I do parentheses? I think it's parentheses. Okay, so we're going to import the vector store index, which, as I was saying earlier, is their base vector store index. And then we're going to also get the keyword index, so simple keyword table index, as well as the, I believe we also need a directory loader. Yep, directory reader, an LLM predictor. Yep, the service context and the storage context. So I'm going to pause right here to, oh no, one more thing, sorry. From LangChain, where is this in LangChain.lms.openai, right, import OpenAI chat, there we go. Is this going to yell at me? Oh, it's not, okay. So a while ago when I was doing this, LangChain was like, oh, we deprecated OpenAI chat, and then they undeprecated it. So I don't really know what's going on with this. There's a lot of dependencies here, but anyway, this is for your vector store index. So this is for creating, something to search your vector store on. This is the router. Oh my God, I didn't explain the architecture last time. I just shut down the window, didn't I? Let me pull this back up. Here it is. Okay. Share screen. Okay, you guys can see this, right? Okay, cool. So this architecture, I forgot to explain this last time. I just like pressed escape on my screen and then just jumped directly into the code because I was too excited. So what we're going to build is this multi-document querying architecture. And what's actually going to happen is you're going to take your query. It's going to decompose your query into multiple queries. And it's going to do that using the LLM. And then it's going to send this back, and it's going to look into first an index that is a keyword index. Essentially, what we want to do with this keyword index is we want to route the searches to the right vector engine. We want to route the searches to the right vector store. And so it looks like there's only one vector store in this diagram, and that's my bad. Well, it's a little more complicated than that. There is one vector store, but this vector store has multiple pieces in it that are each separately hooked, I guess, separately connected to each keyword in this keyword index. And in the keyword index, what we do is we essentially give it a bunch of keywords about a bunch of documents. So if we go back and we take the American cities example, we would go and we would say, like, let's get some information about Seattle, Houston, New York, LA, et cetera, et cetera, et cetera. And we're going to store their information in a vector store. And then we're going to route the queries based on what the keywords are. So maybe your keywords for Seattle are Seattle, Space Needle, rainy city, something like that. Maybe your keywords for New York are like Fashion Week, New York City, Big Apple. I don't know, something like that. You can kind of adjust the keywords as you need. So once you have the keywords in there, they route it to a vector store. The vector store says, oh, I found so maybe an example would be like compare and contrast the airports in Seattle and Houston, which is the example I typically use for this program. And what you can do there is you can say like, oh, well, what we're actually going to do is we're going to go look and we're going to break this down. We're going to break this query down. We know we're looking for airports. We know that we're looking for Seattle. We know we're looking for Houston. So first I'm going to go find out about the airports in Seattle and then the airports in Houston. So first I need to find Seattle, and then I need to go in and look into Seattle's vectorized representation and look for airports. And then Houston in the keywords and go in and look for the vectorized representation of that and look for airports as well. Once we get these chunks of text back, we send it back to the LLM, and the LLM says, okay, well, what you initially looked for was the airports. So I only need the information from the airports from these cities, and I will give that back to you in a human readable context. So that's what the architecture looks like. Essentially, you're going to send it to a query decomposer, which is going to split your query into different parts as needed. And then it's going to go into a keyword index, which is going to route your queries to the right vectors, to the right vector store entries. And then it's going to search those vector store entries for the information that it didn't get, that it needs, that didn't get from the keywords that it needs. And then it's going to send everything that it scrapes and back to the LLM. And then the LLM will organize everything for you. Okay, let's get back into the code. Okay, so this simple keyword table index is the keyword index import that you need to route your queries correctly. The simple directory reader is just to read a directory. The LLM predictor is going to be passed into the service context. Essentially that's your decomposer. The service context allows you to pass in many different, service contexts, such as an LLM, as well as something like an embeddings model. And then you have the storage context, which allows you to pass in ways that you store information, such as a vector database. And this is how we use OpenAI. We're going to use it through LangChain. Okay, so let's see. The next section here, we're going to do our imports. So we're going to import everything that we need for our model. Sorry, not imports. We're going to do our setup. So we're going to set things up. Import.m, import os. Oops. .load.env, and then os.get and OpenAI. Do I have it as one word? I think it's one word. API key. There we go. So this is me grabbing my OpenAI key from my environment variables. Actually, we also need a few more imports here. So we're going to import some things along the way here. Milvus vector store. Oops, that's not right. Milvus vector store. There it is. Okay. There's another import we need here. What is it? From Milvus, we need from Milvus import default server. Okay, cool. So now we have our OpenAI key loaded up, and we have our Milvus stuff ready. So then we're going to do default server .start. So this is where we start Milvus. So you can run Milvus directly in your notebook, theoretically. This should take less than a minute to start, theoretically. I've had this take up to a minute to start. So I'm actually going to use this section here where we're going to just take a pause. And if there's any questions about the code so far, I can field like a couple of different questions.
Not many questions from the audience so far, but if anyone does have any questions for you, Jan, please do ask them in the chat now. I actually have a question for you.
Yes.
So can you just talk a bit about like who might care about this stuff? So just to talk a bit more about the use cases. So you mentioned ideas about looking at internal documents. How does that work? Who needs to care about it? Yeah, who wants to build this stuff?
Yeah. So I mean, like when it comes to building something that's like, if it's going to be over internal documents, your stakeholders are really like, I mean, at the end, everybody's stakeholders are the customers. But when it comes to internal documents, your stakeholders are like the people who are going to use your chatbot. And you kind of want to think about things like, how are these people going to search this stuff? What are the retrieval patterns? It's very similar to just designing anything where you're going to work with a database, right? You have to think about retrieval patterns. You have to think about how are people going to be using this? When are they going to be using it? What are they going to be using it for? And what is the value that this really provides for people? And so I think that it's kind of tough to give a single answer for a broad scale, but I know that like with internal documents, a lot of companies are using this so that they can cut down on the time that people spend searching for things. So we have a lot of people who come to us and ask things about, I don't know if I'm allowed to talk about. We have a lot of people, I can't give any specific examples, but we have a lot of people who come to us and talk to us about what they're doing with these kinds of retrieval things. And it's mostly internal search right now. Some people are doing it for external search. I quite recently talked to someone who's doing something very interesting with this, where they're doing it for external users to be able to search their internal docs or something like that. And I was like, well, that seems very dangerous. Like you're exposing a lot of information there, but I don't control what other companies do. So that's kind of what I see. A lot of this is like, people who want to save time. That's really the short answer. This is taking a really long time to start. So what I'm actually going to do here, I'm going to stop this and I'm going to do something that you probably, this is a trick. So if you are ever running into an issue, you can just delete your folder and hopefully this should start pretty quickly.
All right. While that's running again, we do have a question from the audience now.
Yes.
So Alex is asking, what's the difference between Chroma, Pinecone, and Milvus? So for context for everyone else, Chroma and Pinecone are rival vector databases. So I guess, what's the Milvus pitch in comparison to your competitors?
I would say that actually Chroma and Pinecone are very different from Milvus. When you first look at vector databases, it's very easy to say like, oh, vector databases, like we're looking at a vector database. It's all the same, but it's actually quite different once you start poking into the internals. So if you're familiar with regular database systems, I'm going to do some comparisons to like SQL or NoSQL databases so that you can get an understanding here. And this is really embarrassing because my Milvus server is breaking on me. Anyway, the main thing with Chroma is that Chroma is a very, very fast embedded database. Chroma is something that you want to use when you want to do something server side. You want something that is going to be sitting directly on your server. It's going to be, not server side, client side. It's going to be sitting there almost directly in your front end. And it's going to be kind of like Redis, right? It's not something that you're going to put, it's not something that you want to use for your single source of truth. But if you need some quick similarity search, Chroma is very, very good. And Chroma was founded by MLOps engineers. So Chroma is ML engineers. And so Chroma is very ML oriented. And Chroma has a vector embedding. They have a take on vector embeddings that a lot of other companies don't.
So just to clarify, so it sounds like Chrome is a bit like the SQLite database, if we're doing analogies with SQL databases.
Yeah. It's kind of like SQLite. It's kind of like Redis. It sits directly. It's there for you in your client side. Pinecone is closed source, so I can't speak to anything that's going on underneath the surface in Pinecone. But I can say that based off of what you can buy on Pinecone, what they have available for sale, Pinecone doesn't scale past 16, maybe it's 32, what they call CUs. And what this essentially, like Zillus, you can do like 96, 100 something, you can go really high. And the reason that this is different is actually because of the implementation details of how the servers are implemented. So Pinecone is a single instance, is a very class. It's like MySQL. Okay, if you think about like MySQL, oh my god, I broke this many times now. Okay, I don't know what's going on with this. This is maybe it's because I have it running in another. Do I have this running in another tab? Oh, I do. Oh, that's gonna break things. Oh, haha. Okay, that's my fault then.
It's always fun debugging these things live. So
debugging number one, make sure you don't have multiple instances running at the same time because it's gonna break. But now it's running, so now it's working. Anyway, Pinecone is like MySQL. Pinecone is like, yeah. So I can't speak a lot about Pinecone because I can't see the internal details. I can only tell you from what I can see from what I can buy on the website. That's all I can really say about Pinecone. Milvus is like a cockroach DB. So if you know like cockroach DB, they are a fully distributed system, multiple nodes kind of backend. And that's what Milvus is. Milvus is a fully distributed system kind of backend. So Milvus is actually stateless. It uses whatchamacallit, a coordinator, a set of coordinators and a set of nodes, and the nodes are completely stateless. The nodes only contain data during data reading and retrieval. Now, I can't say that Milvus is entirely serverless because it is not entirely serverless, but all of the nodes that Milvus uses are stateless, and it's written with a distributed system architecture in mind in the background. And so the main advantage that you can kind of think about with this is, or the main difficulty that you can think about with how do you move from a single instance scale up where you can scale up your database, up your GPU, CPUs to a distributed system, is that the distributed system has these, has already thought about in mind, what do I need when I need to shard my data? When my data becomes too big, how should I keep track of what is the single source of truth for my data and where is it stored on the nodes and A, B, C, D, E, F, G. So as you kind of like build out your system, one of the, I guess the first problem that you'll probably run into is that as you write data, you're not going to be able to find your data as you grab it. And so Milvus has this kind of like built into mind into the example. So Milvus from an implementation detail is much more, is different, right? So you're, instead of scaling up multiple instances of the same CPU, you're scaling in multiple instances at different nodes. So yeah, that's the main differences between Chroma, Pinecone, and Milvus as far as I know.
Okay, so in terms of scaling, like does this mean it's about having more documents or having longer documents in there? What's the deal? Like, when do you have to start caring about the architecture of your vector database?
Yeah, scaling is about both. Longer documents, more documents. Actually, the way that you embed and the way that you chunk, we could do an entire day-long seminar on that. Like, that thing is like so complicated right now, and the reason is just because no one's figured it out. No one's figured it out yet. But scale kind of happens at about, I would say, from our tests, from what I've seen, from what we've been able to run, is at about 1 million vectors, you start seeing performance differences. About 1 million vectors of about 1,000 dimensions, you start seeing performance differences. At 10 million vectors, pretty much the only 2 vector databases we were able to even run at 10 million were Zillus and Pinecone, or Milvus and Pinecone. And then once you get past 100 million, well, I haven't been able to run Pinecone at that scale. So I think scale is important for any software engineer who has strong fundamentals to think about. Like, right, like when I was at Amazon, even when I was like interning at IBM, like one of the things that they told us is like, hey, like, when you write software, make sure that you come with a design doc. And in your design doc, make sure that you talk about extensibility, scalability, reliability. Like, is this going to be able to handle a billion vectors? Like, what happens when we have a billion like documents? And that's not an unlikely scenario, because the amount of documents that companies have now is just insane. Like, people, like, data is basically people's entire moats. They're like, we have the data, that's their moat, and that's only going to get bigger. Like, the amount of data that people need is only going to get bigger. So I think that you need to be thinking about scale from the start.
Okay, that sounds like very good advice. Is figure out where the limits of your software are going to be. There is one more question from the audience. I don't know whether you want to continue coding, and then we'll take more audience questions at the end.
Okay,
We got 15 minutes left.
Yes. Okay. Let me try to code this out in 15 minutes. So, where is my code? Here it is. Okay. Vector. Okay. So first we're going to create a vector store, and we're going to make this a Milvus vector store. And no. There we go. Okay. I have a tendency to hit curly braces. So anyway, host. We're going to make this localhost. Port should be equal to default port. So default server dot listen port. Yeah. And then dims, or dim, I guess, 1536. So I've created some. Oh, wow. Okay. I've created something here that has 15. Oh my God, it's yelling at me. Okay. This is because I have an existing connection already. I should have shut down Milvus in my other one earlier. This is what I get for running multiple instances. All right, let's try this. No. Stop. Okay. Okay, let's see if this works. Oh man, I just ran this right before the webinar. This is not great. Uh-oh. Failed connecting to, oh man, I don't like this. Okay, so what I'm going to do here, because I don't want to debug this in the next 10 minutes, what I'm going to do here is I'm going to show you the code that worked, and then we're going to walk through that. How's that sound?
Yeah, at this point, let's have a look at the end goal. Like, what can you show us what the point of this is and how it's it should work in theory?
Yes, I will show how this should work in theory. This is like, so I literally was just running this like right before, like 20 minutes before it. I was like, hey, it's working. Okay. Okay, so this is pulled up, same code. Nice. Okay. So this is what's actually supposed to happen, is you're supposed to do this, and it's supposed to create it quickly and not give you any errors. And then what we're going to do next, when you'll see this in the GitHub, is that we're just going to get a bunch of cities, a list of cities in North America. So this originally started off with Seattle, but I went to Toronto and gave this presentation, so they asked me to add Toronto on here. This section here, you don't really need to pay attention to unless you care about how you scrape Wikipedia. This is just how we scrape Wikipedia. We're just hitting up all their APIs and getting all the information back. This section you probably want to care about. This is how we load the documents into this is creating the first dictionary. Essentially what this is doing, this is mapping the documents as Llama Index natives. So Llama Index is a native type called document, which I think, my personal opinion, is not a great native, but hey, whatever. They have a way to, we're basically mapping these document natives to the title of the Wikipedia document in a dictionary. So you can think of this as Seattle : everything about Seattle. And then we're going to go and we're going to make our context. So you'll see that I have these separate into two things, but they really should be in one. I guess it doesn't really matter. It's up to you how you want to separate them. But we're going to use an LLM predictor, which is essentially what we're going to do for decomposition. And this uses the OpenAI chat thing, and we're going to use GPT 3.5. And then we're going to create a service context where we pass in the LLM predictor. And this is where we like essentially just say like, hey, this index, this query should use this predictor. And then here at the bottom, we have, or sorry, in the next slide, the next section, we have a storage context, which is how we pass in the Milvus vector store that we created up here. And then, where am I? Okay, now we're going to create 2 more dictionaries. And so this first dictionary, city indices, is going to map the title of your Wikipedia document or the name of your city to an index. So we're creating a vector store index. This is what I was talking about earlier, where the vectors, you're actually going to create multiple indexes. And so we're going to create a vector store index from the documents available in our cities, like, you know, in the original map we created. And then we're going to create another map which maps the name of the city to some sort of keywords. And in this case, the keywords that we've chosen are Wikipedia articles about city. Not a great keyword set, but this is just an example. You can choose something better. And then we're going to get this thing called a composable graph. And so this is something, a composable graph is something that a Llama Index offers us as a way to, you know, compose, to route things, basically, put things together. So what we're going to do with this composable graph is we're going to say we're going to start from this keyword table index, and then we're going to give it the list of indices in city indices, which we created up here. These are the vector indices, and then we're also going to give it the summaries. This is the max keywords per chunk for the summaries, I think. So then we're going to go and we're going to create something called a decomposed query transform. If you remember the architecture diagram I showed you, there's a query decomposition engine, and so this is what we're creating now in this next few blocks. So this decomposer basically just says, oh, we're going to use the LLM to decompose the query. And now we're going to make, we're also going to get this thing called transform query engine, which is how we decompose the queries and transform them. And now we're going to create our last dictionary, which is called custom query engines. And what this is this is a dictionary that maps all of the indices together. And so this is an interesting one because what we essentially do here is, we say, okay, we're going to create this graph of keywords to vector indices, and then we're going to create another, like, we're going to use the LLM decomposer, basically the graph, to put an index on this index. So it's like super nested. So there's query engine, and essentially we just give it a query engine and we give each index a query engine, right? So we're going through all the city indices that we created up here. Oh, not up here, up here. And we are just saying, like, we're going to use this with the LLM. And then we're going to give it some extra information so we can transform the query. How do we transform the query? We give it the struct summary, which is the index summary, which is essentially the name, the Wikipedia title, blah, blah, blah. And then there's transform query engine, which is essentially how we transform this stuff. And so we pass everything we just declared into this object. And we set this object to, we map this object to the index ID in the custom query engine. And then in the custom query engine, this part, I don't know if you really need to know this part, but this is essentially telling it how we are going to use the custom query engines based on the graph node. This maps things to the graph, to the node, to the root index of your graph, right? So we have a graph that has a keyword index, that has vector store indexes, that has keywords, and they're all mapped together, and they're all going to start at this root node. So that's how this works. This root node essentially gives you the ability to decompose things, and then you ask it a question, compare and contrast the airports in Seattle and Houston, and you print out your response. The major airport in Seattle is Seattle-Tacoma International Airport, while the major airports in Houston are George Bush Intercontinental Airport and William P. Hobby Airport. Sometimes the response will be longer. Once again, this is not deterministic, so yes, this is what it's supposed to look like. Unfortunately, we weren't able to kind of live code this today, but you can try this out yourself, and feel free to reach out to me with any questions on LinkedIn. Okay, let's see if we can take a few questions here at the end.
All right, super. Yeah, we have got a few more great questions from the audience. Thank you for that. Yes, apologies again to everyone for the technical issues. Sorry you couldn't sort of code along, but I think use case is so powerful, it is worth sort of knowing about and following up, because I'm sure you all read tons of documents and you wish you could just have a chatbot answer some questions for you about them. All right. So this question comes from Matt. So Matt says, I love your talk. I'm working on a translation project. So he's translating a book between Ukrainian and English. Could retrieval augmented generation help him out here?
Yeah.
Do you want to give any details? Oh, actually, the question just continued. Could it help reduce hallucinations with translation? Do you want to talk a bit more about how it might work with a really long document like a book?
Yes. So if you want to do this with like a book, I think your best bet is to first if you're using it to generate the book.
It's translating it. So
translate a book. Translate a book. So then what you would want to do is you want to have the Wikipedia entries and all of that stuff put into a vector database. And as you're translating, if the LLM runs across things that it doesn't know or that it doesn't understand, what you can do is, or I guess like what you can actually do is just do RAG straight up and just say, we're going to use this as our source of truth, and we're going to translate directly from there. Now, I guess like I'm not entirely sure on how your translation architecture is set up, so I can't comment extensively on this. But I think my short answer here is that you can do this, and you can use a vector database as your source of truth if you want to use information after the cutoff.
All right, excellent. Yeah, Matt, let us know how the project goes, and if you run into any problems, then be interested to hear about them. I've got another question from Alex. So Alex asks about how does Milvus manage data privacy?
Milvus is open source, so our commentary on this is there's two options for you. One, you just deploy it yourself. Your data never leaves your premises. We never see it. We never touch it. We don't care. Number two is that if you are seriously managing huge amounts of data, Zillis has I actually don't know if it's available today yet, but it will be available, which is where we only control the control plane. We have a product that allows us to separate the control plane from the data plane, and all we do is run the control plane for you. I think there's like a $200,000 minimum, like whatever for that. So it's really for people who have more than like 10 million, 20 million vectors.
Okay, excellent. All right, and so at that, we are at time. Before everyone dashes off, I just want to say we have got a few upcoming events that it'd be great if you could join. So tomorrow, we're doing a session on AI for visual data, so how you deal with computer vision in business. We've got 3 people on a panel answering some questions from me. On Thursday, we've got a webinar about driving learning engagement. So this is for people who are interested in learning and development. And on Friday, we've got an Excel-based code along about visualizing sales data with pivot charts. And after that, next week is ChatGPT week. So we got 3 sessions on getting better at writing ChatGPT prompts and using some of their plugins as well. All right, so hope to see you again in future webinars. Thank you once again, Eugene. That was I love the theory part in particular, just like understanding the architecture of how these things work. That was really helpful. Thank you. So thank you for joining us. Thank you to Reese for moderating. Thank you to everyone who asked a question. Thank you to everyone who showed up today. I hope to see you all again in future